Hey there everyone, welcome back to LeetCoding. In this episode we are going to talk about one of the most awaited topic called dynamic programming. As dynamic programming is a huge topic, so we have decided to create several episodes on this topic which will cover these concepts: 1D DP, 2D DP, grid-based DP, digit DP, DP on trees, DP on graph, DP on segment trees, SOS DP, and there's always a space for your suggestions. So we will be looking at the theory and then solve few interesting problems and provide the link to the practice problems in the description. So don't forget to check the description box. Feel free to use the comment section if you have any doubt or if you want to make any suggestions. We have already released episodes on bittry, heap, binary search, disjoint set union find, recursion and backtracking. So please subscribe to the channel and press the bell icon if you haven't done already, so that you can get the notification to our latest videos. Now before starting with dynamic programming, there's a prerequisite. You should be comfortable with the topic recursion. I will provide the link to the episode of recursion which will cover up the basic theory as well as few standard problems, and a playlist entirely dedicated to recursion. So you can go to the playlist and practice problems of recursion and then come up and start with the dynamic programming playlist. So let us start with the very first topic, which is one-dimensional DP. So what is dynamic programming? Before going to that, we will be looking at a series called Fibonacci series. So most of you must be aware of what Fibonacci series is. So the first term of the series is 0, the second term is 1, the third term can be calculated using the first two terms. So the third term is the summation of these two, which is 1 again. The fourth term is the summation of these two, the second and the third term, which is 2. The fifth term is the summation of third and the fourth term, this is 3, and then 5 and then 8 and then 13, the summation of these two, and then I guess 21 and so on. So this is a Fibonacci series. Now the question is to return the nth term of a Fibonacci series. So in order to find the nth term, let us write a function. The function is f. So f of n is giving us the nth term of the Fibonacci series. Now let us try to elaborate this function. How can we implement it? So we know that when n is equal to 1, the answer is 0. When n is equal to 2, the answer is 1. But when n is greater than 2, the answer is f of n minus 1 plus f of n minus 2. So this is how we calculate the nth term of a Fibonacci series. So this is recursive in nature. Can we code this? Let us try to code this. I am writing the function f int f. It is going to take an integer n. If n is equal to 1, return 0. If n is equal to 2, return 1. Otherwise return f of n minus 1 plus f of n minus 2. Let us call this function and print the value which it returns for n is equal to 7. Basically the 7th term of the Fibonacci series. It is 8 and it is correct. We already saw this. So 8 is in fact the 7th term of the Fibonacci series. Now let us see how this recursion is working. We wanted to calculate the 7th term. So in order to calculate the 7th term, a recursive call was made to calculate the 6th term and the 5th one. When we wanted to calculate the 6th term, a recursive call was made to calculate the 5th and the 4th term. And when we wanted to calculate the 5th, a recursive call was made to 4th and the 3rd term. To calculate the 4th term, the 3rd and the 2nd term, here the 2nd and the 1st term. So these two were the base cases. They returned the answer, then the 3rd term was calculated and the 5th term was calculated when this returned the answer using the 3rd and the 2nd term. So we can see that when we wanted to calculate the answer for n is equal to 7, we calculated the answer for n is equal to 6 and n is equal to 5. And when we wanted to calculate the answer for n is equal to 6, we calculated the answer for n is equal to 5 and n is equal to 4. So can we see that the answer for n is equal to 5 is being calculated twice. Similarly, For n is equal to 4, the answer is being calculated twice. Not only twice, it will be calculated once again here. So n is equal to 4 will be called here and 3 will be called here. Similarly, when we look at 3, the answer to 3 is being computed here. It is being computed here. It is being computed here as well. So there's a lot of repetition in this. So why don't we save the answer for any specific n once we calculated it, so that we don't need to calculate it again. We already calculated the answer for n is equal to 3 here. Why to calculate it again here? So that is why once we calculated the answer for n is equal to 3, we will be saving it somewhere so that we don't have to calculate it again. So this call will not be made once we calculated the answer for n is equal to 3. Similarly, when we calculated the answer for n is equal to 4, this call will not be made, and this call again will not be made. And when we calculate the answer for n is equal to 5, this call will not be made. So similarly, we will save a lot of time recalculating the same values again and again if we try to save them. So let us try to save them here. Let us create a vector of type integer dp, and the size of this is 100, and let us initialize this with -1. To this function s, we are sending this vector as an argument, and to these function calls as well. Now what we need to do is, we have initialized this dp with -1. -1 indicates that the particular state of a dp or the particular index of a dp is empty, so nothing has been kept there. And let us say if we calculated the answer for nth term in the Fibonacci series, we want to store it. We want to store it at the nth position in this dp. So once dp of n is calculated, it is being stored at dp of n. And the next time when the same call is made again, we are going to return the dp. So if dp of n, if it is calculated, so if it is not equal to -1, it is calculated, and we are going to return dp of n. As simple as that. Let us try to run this. We got the same answer, but here what is the difference? The difference is, when we were calculating the answer for 7, a call was made to calculate the answer for 6. When we wanted to calculate the answer for 7, a call was made to calculate the answer for 6. Then to calculate the answer for 6, a call was made to calculate the answer for 5 and 4. Then here 4 and 3, here 3 and 2, here 2 and 1. So both of them returned the answer for 3, and dp of 3 was now saved as 1, and it was returned to dp of 4. Now when a call was made to dp of 2, it returned 1 and it returned 1 again. So dp of 4 was saved as 2 and it returned 2 here. And a call was made again to dp of 3. So as it was already present inside the vector dp, so 1 was returned from here and 2 came from here. So it is 3. dp of 5 was now saved as 3. It is going back again, sending 3. Now a call was made to calculate dp of 4, which was already present inside the dp array or the dp vector. So 2 was returned from here and 3 came from here, so it is 5. So dp of 6 is equal to 5. It was sent to 7. Now 7 made a call to compute dp of 5, but dp of 5 was already present inside this, so further calls were not made, and the answer was returned from here. The answer was 3, and 5 plus 3 is 8. So dp of 7 was saved as 8. So these are the values that are being stored inside the dp. Obviously we can also save the value for n is equal to 1 and n is equal to 2, but we are simply avoiding it. There's no need to save them. Now let us simply, before exiting out of this function, print the entire content of the dp array. I is equal to, I is smaller than 8 and I plus plus. Cout dp of I. It is going to print whatever is there inside the dp array. This is dp of 0, dp of 1. dp of 0 is nothing because we are not considering a sequence where n is equal to 0. We are starting with the sequence 1. So this is the dp of 1, which is not being stored. dp of 2 is also not being stored inside the dp. dp of 3 is 1, dp of 4 is 2, dp of 5 is 3, dp of 6 is 5, and dp of 7 is 8. So this is the content of dp. Now this is called memoization. We are simply memoizing the solution for a particular state n. Now can we convert this memoization into dynamic programming? So it's very simple. We are just filling up the dp array, and we are doing it with the help of the previous two terms of the dp array. So instead of calling this function, what we can do is we can set dp of 1 is equal to 0. The first term of dp is 0. dp of 2, the second term, is equal to 1. Now we can start calculating from the third term of the dp. I is equal to 3. I smaller than equal to, we wanted to calculate till the seventh term, so smaller than equal to 7, and I plus plus. dp of I is equal to the summation of previous two terms of dp. So dp of I minus 1 plus dp of I minus 2. And finally we can see out dp of 7. And we can erase this function because now we don't need this. Alright, so we got the correct answer. Now this is called dynamic programming. We are using the previous states to calculate the current state. Now we can observe one thing. This solution is very good when we want to have all the terms in the Fibonacci series till n. But let us say we only want to calculate the nth term and we don't want the term from the starting till the n minus 1th term. So for that, what we can do is we can see that we only need the previous two values and we don't need the values which are smaller than I minus 2. So instead of creating an entire array, we can only create two variables: a, the first term, which is equal to 0, b, the second term, which is equal to 1, and now we can calculate the third term, c, as the summation of a plus b. And now we can update a, which is the first term, to the second term, b, and we can update the second term to the third term, c. And finally we can see out b. And it is giving us correct answer. So we saved a lot of space. From big O of n extra space, we made it a constant space solution. Although the time complexity is going to remain same, but the space complexity improved a lot. So this is what dynamic programming is. We are saving the values for the states which are already computed so that we don't have to compute them again. Now let us go and see a few problems. The first problem is climbing stairs. So you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb one step or two steps. In how many distinct ways climb the top? If you want to see what the problem is saying, we have these stairs and we are here at the 0th stair. This is the first, second, third, and the fourth. We want to reach the top. So what we can do? We can climb one step at a time. So this is the first step. Or we can climb two steps at a time. Now we are either here or we are here. So if we are here, we can climb again one step at a time or two steps at a time. And if we are here, then we can climb one step or two steps and we can reach the top. So we have to calculate in how many ways we can do this. Let us try to see a smaller example so that we can actually compute it. So if the number of stairs are 2, one stair and the second stair, this is the 0th stair, this first and the second, and we are here at the ground. The first way is to go to this step and then take one more step to reach the top. The second way is to directly go here. So there are only two ways for this configuration. Let us say we have 3 stairs, first, second and third. This is the ground level and we are here initially. Once we reach here, the second one is we reach here. From here we can reach to the top. So this is one of the way. The second way is reach till this point and then reach the top. This is the second way. The third way is to go once, twice and thrice, one step at a time and reach the top. So this is the third way. So I think for n is equal to 3, the answer is 3. Yes. Now let us try to solve this problem recursively. So can we say that if we are at a particular step n. So for the nth step, let us take some other variable because we want to reach the nth step. Let us say we are at the x step. So the answer for this will be equal to the number of ways to reach the top from x plus 1 plus the number of ways to reach the top from x plus 2. So this is how we can calculate the answer, and we can see that this problem is also very recursive in nature, and we can try to solve this using recursion. Int help int x, where x is the step we are currently on and n is the step we want to reach. If we reach at the nth step, we can simply return 1 from here because we reach the top. This is one of the way. If we exceed the topmost step, so if x is greater than n, then we can simply return 0. Or we can say if x becomes n plus 1. This is not allowed, so we are going to return 0. This is a false configuration. Otherwise, we can return help of x plus 1 comma n plus help of x plus 2 comma n. And we can call this function return help of 0 comma x. Let us try to see 0 comma n. It is giving us correct answer. Now let us try to visualize the recursion tree for the same. So this is our x, which is equal to 0. This is our n, and to calculate the answer for this, we need to go to f1 and n and f2 comma n. To calculate the answer for this, we need to go to 2 comma n, f of 3 comma n, and to calculate the answer for this, f of 3 comma n and f of 4 comma n. So again we can see a lot of recomputation here. So this is a recomputation, and this is again a recomputation. So there's a lot of repetition here as well. So we can apply DP, or we can apply memoization first. So we will create a vector of int v, which is of size, let's say here the constraints of n are 45, so we can create it of size 100 to be on the safer side, and initialize this with -1 and send this to our function help. So we are sending this v, a vector of integer, and v, it is initialized with -1, and if we calculate the answer for any particular x, we are going to save that. V of x is equal to this, and if we already have answer to a particular position x, if v of x is not equal to -1, then return v of x. Let us try to submit this. Here we have to pass v. Now let us try to submit, and we are getting correct answer. So this is the memoization code, or the top-down code. Now we need to convert this into the bottom-up code. So to calculate the answer for any particular state x, we need the answer for x plus 1 and x plus 2. So first of all, dp of n, when x is equal to n, this is equal to 1. dp of n plus 1 is equal to 0. Now we need to find the dp for I is equal to n minus 1, I greater than equal to 0, and I minus minus. dp of I is equal to dp of I plus 1 plus dp of I plus 2, and we need to return dp of 0. And this vector is dp. Now we don't need this recursive code, and we are getting correct answer. Now this problem is actually same as the Fibonacci that we already calculated. We need only the next two terms to calculate the answer for the current term, and we can think it in the reverse fashion as well. We need the answer for the previous two terms to calculate the answer for the current term. So this is nothing but same as the Fibonacci series. Now we can move on to the next problem. Also, you can optimize it by using only two variables because we only need the next two terms or the previous two terms, the same thing that we have done in the Fibonacci. Now we have the next problem, the coin change. You are given coins of different denominations and a total amount of money. Write a function to compute the fewest number of coins that you need to make up the amount. If the amount of money cannot be made by combining all these coins, then return -1. You may assume that you have an infinite number of each kind of coins. So let's take an example. Let's say we have the coins 9, 6, 5 and 1. These are the coins that we have, and we have infinite number of each of these coins. The amount that we want to make using these coins is 13. So if we want to think in a greedy manner, so what we will be doing, as we need minimum number of coins, we will think that let's take the biggest coin first, which is 9, and after taking 9, the amount that remains is 4. Now how can we make 4? So 4 could only be made by using 4 coins of value 1 each. So the total number of coins that we end up using here is 5 in this case. But if we take the coin 6 twice, and it will give us 12, and then we take the coin with the value 1, it will give us 13. So 2 into 6 plus 1 is going to give us 13, and the number of coins that we use is 3. So this is much better. So that's why we cannot go in a greedy way. We cannot think that let us take the coin with the greatest value first, and then we will take, and then with the second greatest value, and so on, because that is going to give us the wrong answer. So that is why this problem is again a brute force problem. We have to search for every possibility. But we will see that if we take all of these possibilities, there will be some repetition, and we can apply dynamic programming. So let us try to write a recursive code for this problem as well. Int help int. So this is the amount that we want to calculate. Then we will have a vector of int coins. If amount is equal to 0, then how many coins do we need? We need 0 coins. We don't need any coin if the amount is 0. Other than that, we will look for each of the coin that we have. For I is equal to 0, I is smaller than coins, I plus plus. If we can take this coin, we can only take this coin if our amount which is remaining is greater than or equal to the current value of the coin. Then we can take this up, and we can have one of the option is equal to 1 plus going ahead by taking this coin. So the amount will be reduced by coins of I. So this is one of the possible option. And similarly, if we have another coin which we can take, we will have another option. So we have to calculate the most optimal option. We will create an answer which is equal to int max, and we will try to minimize this. So answer will be equal to minimum of answer comma this option, and let us compute this option just above this. So this is our most optimal answer, and we are going to return this. Let us try to return the help of amount comma coins. Let us see if we have any compilation error. This we are not declaring the option. So we are getting correct answer. Let us try to submit this. Hopefully we will get a TLE. Runtime error because there is an overflow. Alright. So we had an overflow. Let us take this int max by 2 so as to avoid any overflows. Let us try to submit this now. In the case when we are not getting any answer, so this is one of the case when we are not getting any answer, we don't have to return int max. So as here we are returning int max by 2, we don't have to return that value, but instead of this we have to return -1. So we will see what answer we are getting. So this is the answer that we will be getting, and if this answer is equal to int max divided by 2, then we can return -1 because there's no possibility, otherwise we can simply return the answer. Let us see if it works for this case. In this case the answer should be -1. Int max by 2. Yes, we are getting -1. Let us try to submit this, and we are expecting a time limit exceeded. and here we have TLE. Because there's a lot of computation that we are doing again and again, we need to save that. So in order to save that, we will create a vector or an array to do the memoization, and the state that is changing here is amount. So amount is the state that we need to memoize. The limits of amount is 10 raised to the power 4. So we will be creating int dp of 10 raised to the power 4. We will initialize the values of this dp with -1. Memset dp -1 size of dp, and when we are returning this, we will be saving dp of amount is equal to answer, and before this, if dp of amount is not equal to -1, then return dp of amount. Let us try to run this now, and we are getting correct answer. Let us submit. So it got accepted. Now which state do we memoize? So the state which changes in each recursive call is the one that we need to memoize. There might be 2 such states or 3 such states. So we will be talking about it later when we will be covering up the 2D DP and the grid based DP. But as of now, we have only one state that is being changed here, which is amount, and we are going to memoize that. So this is the memoization solution. You can convert the same into the dynamic programming solution. So you just have to do the same that we did in the Fibonacci solution and in the climbing stairs. So you have to write the code here, creating a vector, and do the same steps, and you can see if there's any scope of optimization. But in this case, there won't be a scope of optimization because you will need all the previous states to calculate the answer for the current state. So this is it for the video. I will provide more practice problems in the description, so you can go there and check the description. If you like the video, please subscribe to the channel, like the video, share it with your friends. Thank you.